All right, Assalamu alaikum and good afternoon. So this is the third lecture of a series of 4 lectures about multigrid methods in scientific computing. And before I start on with the main agenda for today, I would just go about doing a small recap of what we've done in the first 2 lectures. So the first lecture in the series was where we explored iterative methods, and specifically iterative methods for large linear systems that came out of PDE discretization, and that PDE discretizations were mainly of the finite difference type. When it comes to PDE discretization of the finite difference type, especially we have our experimental testbed for the 2D Poisson equation, which we are using throughout for making the theoretical points for iterative methods that come along the way naturally in the course of developing multigrid methods formally. So we discussed nested iteration and defect correction, and we saw up how Gauss-Seidel and Omega-Jacobi type of basic iterative methods seem to suffer and stall whenever you have a reasonable resolution of the partial differential equation into a discrete problem. And if you don't have a reasonable resolution, then the numerical solution is of no good use. And we dissected it, a 1D Laplacian problem, and we saw that we have the error, which could be expanded in the form of a linear combination of frequencies, and allow me to call those frequencies eigenfunctions of the original operator, and coincidentally eigenfunctions of some of the basic iterative methods such as Omega-Jacobi. It gave us a perspective on how to expand the general error that was in, say, a normal Euclidean space R into an alternative basis. By an alternative basis, I mean a basis that consists of eigenfunctions of the operator. And since the operator is diagonalizable, which is one of the desired properties in most of the theoretical investigations we have, because if we don't have diagonalizability, we have to have more complicated add-ons to multigrid, such as preconditioning and other stuff. So if we do have diagonalizability, we could be sure that the discrete operator that we get has a complete set of eigenfunctions, meaning if it has n columns, it has n linearly independent eigenfunctions, and therefore we can just call ourselves lucky that Omega-Jacobi has the same eigenfunctions as its own eigenfunctions as well. So it's easy to analyze how Omega-Jacobi would fare when it's used for iterative solution of that linear system. Then we saw in the first lecture how might we break up those eigenfunctions into 2 sets, which aren't always equal in number. That's a discrete set. It's not always half and half. In 1D, it's half and half. In 2D, it's a quarter and 3/4. And how might we call one set of eigenfunctions as a set of low frequency eigenfunctions, others as a set of high frequency eigenfunctions. And high frequency eigenfunctions are the ones that are rapidly reduced by stationary iterative schemes, such as Omega-Jacobi, Gauss-Seidel, SOR, and others. Whereas the low frequency eigenfunctions, the components of the error along the low frequency, along the expansion in the low frequency eigenfunctions, they seem to stall, which causes all of these stationary methods, the classical not all of the stationary methods, but I just realized my mistake, because multigrid is also a stationary method from the definition of a stationary method, but it causes the classical stationary methods to stall. And multigrid multigrid is a combination of fundamentally different ideas, two different ideas which could be classified as nested iteration and coarse grid correction, clubbed into one to form a very cohesive algorithm which circumvents the difficulties that omega Jacobi or Gauss-Seidel type of iterative methods bump into. It circumvents those, and then it goes on for rapid convergence. And when we say rapid convergence, it's nearly linear convergence, a linear residual decay. Then we cooked up that algorithm in the first talk. That algorithm was a two-grid algorithm, which meant that we were only, for the sake of simplicity, using two grids, a fine grid, a higher resolution fine grid, and a substantially lower resolution coarse grid, and how we could set up different procedures on these two grids in order to come up again with a cohesive algorithm, which is known as the two-grid algorithm. And any algorithm, any multi-grid algorithm, so as to say, which uses more than two grids, would only converge up to the results that a two-grid method gives. So the two-grid method, from an accuracy viewpoint, is the most accurate. But if you choose to solve the coarse grid problem, not exactly, but recursively through the same two-grid algorithm applied yet again, and again, and again, and again, until you reach a coarsest level that you dub a simple multi-grid V-cycle. Okay, so a multi-grid V-cycle may be faster than a two-grid cycle, but it can never be more accurate. Then in the final part of the first talk, I showed you an implementation of the basic multi-grid algorithm that solves a two-dimensional Poisson equation. I ran it using the iterative method of Jacobi, using the iterative method of Gauss-Seidel, and I also showed you how multigrid would treat such a problem. One of the fundamental benefits of using multigrid is that it's not resolution dependent. It's mesh independent. It has a mesh independent convergence rate. So we saw that if we had a very coarse grid and a problem set up on a ridiculously low resolution grid, a very coarse grid, so maybe just 8 divisions or 4 divisions, then you could iterate and solve that problem using any classical stationary iterative solvers in a trice. However, as soon as you make the resolution reasonable, meaning you have lots of choppings in your domain, lots of discrete choppings, the problem becomes high resolution, and that's precisely the point where Gauss-Seidel and Jacobi type of classical stationary methods tend to stall. However, multigrid was mesh independent. So it wouldn't matter if it causes residual decay, say in 10 iterations, 1 order of magnitude per cycle. It would roughly keep on that same order without any regard to the kind of resolution you had. So if you have 8 points, or well, let's be reasonable, no, 8 points, let's say we have 64 points or 64,000 points, the convergence rate of multigrid is roughly the same. This marked the end of the first talk. In the second talk, we tried to analyze the iterative behavior of multigrid. And since multigrid is a rather involved algorithm, it has many different procedures across a variety of grids, which again, for the sake of simplicity, for the sake of analysis, and keep the analysis simplified and accessible, we just use a pair of grids, which is one is fine and the other is coarse. And usually the coarse grid has a mesh size which is 2 times the mesh size on the fine grid along each dimension. We have a 2-dimensional problem, by the way. So we saw that if we had a classical stationary iterative method and we want to find out its convergence rate, we need to take account of all the frequencies. And since it has eigenfunctions that we already are aware of, we can find out all of its eigenvalues, and the largest absolute eigenvalue, dubbed the spectral radius of the method, would just tell us the convergence rate of that method. And we already know that the convergence rate of Jacobian Gauss-Seidel type of methods, they roughly are equal to 1, which means that as soon as so we now know what happens behind the curtains. As soon as they have eaten up all the high frequency components of the error, the low frequency components, they just sit and smile in the face of these methods, and they just stall. And the residual doesn't come down to 0, which means that it would keep on lingering along the x-axis, not really touch the x-axis. Unless, of course, you have ridiculously lot of iterations, thousands and thousands, or hundreds of thousands of iterations, which is not a practical thing to do. Okay, so when it came to multigrid, the main problem was how to analyze the convergence behavior of multigrid, since multigrid works on multiple scales, or 2-grid works on at least 2 scales. And when we talk of scales, at some point in time, it is important to understand how we transfer information from a coarse grid, from a fine grid to a coarse grid, which is called averaging or restriction, and how do we do the reverse of it, meaning how do we pick information on the coarse grid, transfer it back to the fine grid, which is called interpolation, and in the multigrid jargon, it's called prolongation. So there are a variety of restriction operators, a variety of prolongation operators, and there is a battery of smoothers. And at this point, we need to analyze the 2-grid operator that comes out of the 2-grid algorithm that we set up in the first talk. So to remind you of the 2-grid algorithm, or the 2-grid operator, the 2-grid operator that we had was written up like this. It was something along these lines. Yeah, so this is the smoother, and the new one smoothing steps, meaning you subject the initial guess or the initial guess of the solution to new one runs of the smoother, be it Gauss-Seidel or be it Jacobi or omega Jacobi or some other classical iterative method. And then once you do that, the next step is coarse grid correction, which consists of 5 sub-steps. The first step is to compute the residual after you've run the smoother for the first few times. Once you compute the residual, you have to understand that the residual is on the same fine grid as the original problem. And to bring it down to a coarse grid, you need to average out the residual information on the coarse grid. In order to do that, you have to use an operator, a grid-based matrix operator, which is known as the restriction operator. A restriction operator, this is, by the way, a restriction operator. The restriction operator may do its averaging job in different ways. For example, the simplest one is called injection. What does injection do? It just picks out those points. So we are assuming hierarchical grids for now to keep the discussion simple. And so one of the points, from a funny viewpoint, you hear this setup from me so many times to keep the discussion simple that you might be wondering how complicated does it get. It can get a lot complicated when you analyze it with a lot of accuracy. So what we do instead of coming up with very accurate computations of these factors, we come up rather with using estimate of these factors. So today is the talk that would talk about how do we come close to estimates that are not 100% rigorous, but they have a broad spectrum of applications. Okay, so I'm not yet finished up with what we did in the second talk. In the second talk, we did a rigorous Fourier analysis where we said that we have frequencies that we wrote like this, and those frequencies were k pi xh into sine L pi yh. And these functions, these eigenfunctions, are the eigenfunctions or the eigenvectors that come out of analyzing a characteristic value problems using the Laplacian operator, but inducing Dirichlet boundary conditions, homogeneous Dirichlet boundary conditions. So if you use homogeneous Dirichlet boundary conditions, then you can show, using a rigorous proof, that these are the eigenfunctions of the Laplacian setup in that case, or the PDE operator setup in that case, of which Laplacian is a huge part. When I say Laplacian is a huge part, what exactly do I mean? I mean that I have used the boundary conditions for deriving the eigenfunctions, yet when I do the analysis, I do it on the central operator. But since the eigenfunctions have been derived using Dirichlet boundary conditions when forming the characteristic value problem, I could be assured that those boundary values or those boundary conditions do not actually pose a problem. I mean, they don't pose kind of a problem which would invalidate all the insights that I get out of this rigorous analysis. So this rigorous analysis is, as its qualifier or adjective leads you to think, it's quite rigorous for Dirichlet boundary conditions or Dirichlet boundary value problems. And most of these, well, all of these operators, this operator is the discretization operator on the fine grid. This is the restriction operator. This is the inverse of the operator on the cost grid, discrete operator on the cost grid. And there is an assumption that its inverse exists. And for the most part, we would be interested only, again, yet another simplification, to operators that don't have, that are not singular, that don't have non-trivial, null spaces. And this is the prolongation operator. This is just the identity operator, and these two represent smoothing operators. So we analyzed it. We saw that we have 4 cross 4 matrices. And if we just analyze those 4 cross 4 matrices and find out the largest eigenvalues and then compare all the largest eigenvalues and find out the largest of the largest, we can get a fair estimate of the worst case factor, which is called the 2-grid rigorous convergence factor. So this is what we did mainly in the last talk. And before I start on with, I would just like to subject you all to a very respectful little quiz, starting from, if you remember the exact forms of the Jacobi operator and the Gauss-Seidel operators for a simple linear system. Any simple linear system which could be technically subjected to one of these classical stationary iterative solves. So not all of these linear systems. So for example, if we have, when I say LH versus when I say L, so this is the PDE operator, usually written in calligraphic L, and this is LH, which means the stencil operator that lives on the grid, that exists on the computational grid. And when I say AH, it means a discrete matrix that is formed for each point, that has a row corresponding to each point on the grid, and it incorporates all the boundary conditions in it as well. So this is just a small recap again. So this is the matrix where you start. And once you have this, what you have next is AH, UH is equal to BH. And when I say AH, I mean it's such an AH come out of such a PDE problem that it is amenable to a classical stationary iterative solve. Meaning, if we had all the time in the world, many computational hours on a computational server, we can typically run Jacobi and Gauss-Seidel as many times as you'd like until the residual is negligible. Okay, now how do we construct a simple Jacobi. A Jacobi method is, well, a Jacobi method requires that this be diagonally dominant and be positive definite. Both Jacobi and Gauss-Seidel do require that. Diagonal dominance, by the way, is a sufficient condition. Being positive definite is a necessary condition. Okay. So it's speculated, but not currently very clearly known for all the different kinds of matrices that could prop up when you are discretizing PDEs. What forms a set of necessary and sufficient conditions? So we have necessary conditions, we have sufficient conditions, but we would love to have necessary and sufficient conditions. Fortunately, we don't have that. Okay. And we make too strict a condition if we just take a conjunction of those, if that's what you're wondering, Azim. So that's not the case. All right, so when you come up with, you break this matrix and you come up with multiplicative factors, the regular term that we used in numerics for that is decomposition. So if, for example, the LU decomposition, factoring up of this matrix X, AH into two factors, one which is lower triangular and the other which is upper triangular, typical LU decomposition, which is what most software implement. Looking at your matrix, they analyze your input matrix, they see what nice properties, if any, it has. If it's an M matrix, if it's a diagonal-only matrix, called a Toeplitz matrix, if it's a circulant matrix, it'll come up of what maybe it would decide. Most intelligent and smart software would decide what kind of decompositions to make in order to give you an exact solution of this, if an exact solution is what's desired. We don't desire an exact solution for now. We want to set up a Jacobi method. So we break it into these three matrices. One matrix we call D, which is just the main diagonal of this. And if you just delete the main diagonal from this, then the lower triangular part that you get is called negative L conventionally, along with a negative sign. And the upper triangular part, once the diagonal's been removed, the strictly upper triangular part is known as this. When you break a matrix into addends instead of multiplicative factors, the jargon that we use, we call these splittings. So we split a matrix A in this form for Jacobi. We huddle up these two, we cluster these two, we let this stay as it is, and then we say we have D minus L minus U, or minus L plus U, UH, which is equal to BH, and this leads to ultimately UH being D inverse BH plus L plus U UH, and we set up an iterative scheme by saying, fine, the next iteration would come out of this former iteration. Now this is what we call a Jacobi method. Okay, if we wish to set up an omega Jacobi method instead, which is very much desired in the multigrid context, what we do is, okay, so this works like this. We would love to call this guy Z. Instead of calling it, we temporarily block this, and we would not call it the final next iterate, or we won't call it the next iterate. We'll call it a temporary iterate called Z, and then we would say, fine, UH, the next true next one, will be a weighted average of what we have, omega times, which is the relaxation parameter, omega times Z, plus 1 minus omega times UH k minus 1. And what you are required to do in order to make up this entire thing just represent it in the form of u h k minus 1. So in the place of the z, you can quickly plug in this entire thing and do the little bit of arithmetic and come up with uh in terms of omega and in terms of uk minus 1. So this iteration, a combination of this iteration, is what we call omega Jacobi. All right. Enlightened? Yeah, this is what we discussed in the first talk, as well as, I believe, a bit in the second one. Okay, so when we are interested in quicker convergence than that, for most problems, what we have rather is AH UH is equal to BH, the same splittings. But now what we cluster is this part, and we say UH kth is, come again? Yeah, that's a mistake. Thank you for pointing that out. So there is a D inverse here. Yep. Thank you, Junaid. Okay. So what we have here is D minus L inverse BH, and what we have here is plus D minus L inverse U times UH k minus 1. So this gives you a matrix based version of what we call Gauss-Seidel Lex, where Lex stands for lexicographic. Okay, we discussed when we expounded on why do we need to have this qualifier lexicographic. We have a grid, and it has multiple nodes which are variables in it. And if we were to traverse or walk on those unknowns, resolving them one by one in one order or in another order or in yet a third or a fourth order, Gauss-Seidel would report different final vectors. Jacobi would report the exact same vector every time, but with Gauss-Seidel, ordering is important. Therefore, we have mentioned which ordering we are talking about. So the ordering is lexicographic, left to right and bottom to top. Okay, with this bit of, I'll also give you the restriction operator IH to 2H. It was 1 by 16, and you had what did you have? A 4 and a 2 and a 2 and a 2 and a 2 and a 1 and a 1 and a 1 and a 1. So this is the full weighting restriction of order 2. And this is the central element on which it's being applied. And prolongation, the bilinear prolongation or linear prolongation in 2 dimensions is its scaled adjoint, nothing more. And by that we mean that if we were to construct a matrix for prolongation, which is a matrix of this shape, all we need to do is to transpose that matrix and scale it with a particular scaling factor. So we've discussed those things. The PDF of those talks is available. So let's now move on to what were the limitations of the rigorous Fourier analysis that we did in the second talk, and how now we need to move on to something more robust. Okay, so as we discussed, we had an eigenfunction The first thing you'd like to observe, it was the eigenfunction for the discrete operator using Dirichlet boundary conditions. And it turned out to also being the eigenfunction for the smoothing operator, which was omega Jacobi in that case. As soon as we have Gauss-Seidel, the first thing, instead of omega Jacobi as the smoother, the first thing that we note is that those product of sign functions is no longer the eigenfunction of Gauss-Seidel, and it could not be applied directly without coming up with a very complicated device. So that was a big turnoff. Moreover, if we have different sorts of boundary conditions, it was non-trivial to cook up or to solve that characteristic value problems using all the variety of boundary conditions we could have. So I'd say the initial first thought of Professor Aki Brandt, who was the inventor or the discoverer of multigrid, let's say, was this: the boundary operators only act on the boundary of the domain, and the boundary grid points compared to the interior grid points are just scant few in number. So let's think of some kind of boundary conditions, and what I am about to say might sound strange in the first, when you hear it at first. Let's come up with a set of boundary conditions which mimics having an infinite grid, having just the interior stencil in the middle of the domain all the time, connecting variables on the computational grid which are neighbors and not thinking about the boundary operators. So as you might be able to guess, being mathematicians, the boundary conditions that represent that are known as periodic boundary conditions. Once you use periodic boundary conditions, what you get are circulant matrices in linear algebra, meaning you have kind of a Toeplitz matrix already, and all you have is just circulation of those same row elements in the next few rows. Yeah, do you register what I'm saying? So Toeplitz matrices are matrices having constant diagonals, right? And circulant matrices are matrices of this kind. So what you have is, just imagine you have something like this: 4, 3, 2, 1, 0, 0, 0, 0. In the next row, you may have 3, 4, 3, 2, 1, 0, 0, 0, 2, 3, 4, 3, 2, 1, 0, 0, and so on. So what exactly is happening? This is getting connected here, this is getting connected here, and what you are getting is circulant, I made a mistake, circulant matrices, 3, 2, 1. So 3, 2, 1, like this, I think, yeah. Yes, so they keep on turning. I mean, what happens basically is the end shifts here in the next, for the next row. And this is how periodic boundary conditions after discretization look. They give you circulant matrices. Circulant matrices coming out of periodic boundary conditions, they mimic an infinite grid very closely. So this was an initial idea of Aki Brandt, that let's just consider the interior operator, good or bad as it is. We just analyze the interior operator. If there are terrible operators or operators of some kind which really requires a bit of cognizance, we would do, first we would devise a suitable realization scheme for all the operators on the PD, but only analyze the interior operator. And if there are operators that need some recognition on the boundary, just do multiple realization steps on those boundary variables, and in the end all we'd have is just mimicking the interior operator, which would still give you a reasonable discretization. Okay, is this point clear enough? I apologize for asking this, but this is crucial to understanding why LFA could even be used for analysis.
Can you repeat the very last line?
Yes. So let me recollect what the last line was. All right, so you may have a matrix which may have very nice rows and some bad rows. And those bad rows of the discretization matrix might correspond to some odd-looking conditions you may have on the boundary of the domain. So original idea of Archibrandt was to first think of what kind of relaxations would solve those boundary equations in a reasonable way. They may be different from what you need to do in the interior, but it's still reasonable. It would still solve them and shove you further towards the solution, push you further towards the solution if that was a reasonable discretization. So his point was, since those boundary points and boundary variables are scant few in comparison to the interior points, you just analyze the interior point, the decay rate, the convergence rate, asymptotic convergence rate, the norms and other things. It would still give you a realistic estimate of how a multigrid method on the combined matrix would work if you just did, if required, multiple relaxations on the boundary unknowns while leaving the interior unknowns intact. It would still converge towards the interior estimate, because at the end of the day, your discretization is reasonable for the boundary grid points. So this was the idea which he came up with. And following this, what I would do today is walk you through the fourth chapter of the book Multigrid and tell you exactly how to do multigrid for various problems. Now, the word or the term that Archibrandt used initially was local mode analysis, and eventually it became local Fourier analysis. Archibrandt, you could say, was the successor of two other mathematicians. One was Fedorenko, probably a Russian guy, and the other's name I've forgotten. Okay, thank you. And they came up with separate ideas of coarse grid correction and nested dissection. What they did not come up with is putting it down together as a coherent multigrid algorithm. Archibrandt did just that. So since Archibrandt came up with the multigrid algorithm of the V cycle as we know, he was also responsible for giving us theoretical tools for its analysis. And rigorous Fourier analysis could not be applied when you have boundary conditions that are very hard in terms of solving a corresponding characteristic value problem. They could not be applied when you have a smoothing scheme, for example, which is based on multiple scales, or a smoothing scheme that doesn't have a constant diagonal or other things, because then the eigenvalues, eigenfunctions of the operator are not shared by the smoothing operator. So there are a few things that we would like to talk about. So let's get down to the basic. The first thing is the local nature of LFA. So under general assumptions, any general discrete operator, nonlinear with non-constant coefficients, can be linearized locally and can be replaced locally by freezing the coefficients by an operator with constant coefficients. Thus, general linear discrete operator with constant coefficients only are considered in LFA. Formally, they are defined on an infinite grid. Now, this has a very subtle meaning. Now, imagine that you do have a diffusion equation, but it's not a constant coefficient diffusion equation. Rather, you have spatially varying functions that are multiplied with the x and the y, second derivatives of x and y. If those spatially varying functions result in a phenomena which is called singular perturbation, which can happen, then some of these methods might not work. But if that is not the case, if they're smoothly varying spatial functions, then what you can do is come up with a representation, a constant representation, maybe an average representation of those functions, have those constants in front of the derivatives and still do a Fourier analysis, which may come up with estimates that are very close to how your actual multigrid would work. So all considerations in the context of LFA are based on grid functions of this kind. When you have LFA and not rigorous analysis, what you have is this. You still call it phi theta x, and it's an exponential function, which means that it's a linear combination of the sine and the cosine function, and a complex linear combination that is. And in fact, this is just a 1D 4.1.1, gives you just a 1D representation of it, but in reality, it could be a multi-dimensional analog. So in the context of LFA, all operators which we talk about, including the fine grid operator LH, the smoothing and intergrid transfer operators SH, IH to capital H is the restriction operator, the averaging operator which transfers information from the fine grid to the coarse grid, I sub capital H super small h is the prolongation or interpolation operator which carries information from a low resolution grid to a fine high resolution grid. The coarse grid operator LH, you have to have some representation of the original PDE on the coarse grid, that is known as L capital H, as well as the coarse grid correction and two grid operators KH to capital H and MH to capital H respectively will operate. So this is one of the important ones. The inner one is just KH to H. So don't get baffled or perplexed. This is KH to 2H. This guy is MH to 2H. So what KH to 2H is missing is just the application of these two operators on its right and left. That is the, इसको हम कहते हैं, this is known as the coarse grid correction operator. These are the smoothing operators, and this is the two grid operator. Okay, so they will operate on these grid functions. These grid functions, which I showed a moment ago, and are considered on the infinite grids, G small h and G capital H respectively. And the goal of LFA is to determine smoothing factors. What do we need to do with LFA? Fine. For the last couple of minutes, you can ask me, you've been talking about rigorous Fourier analysis and local Fourier analysis and iterative methods and multigrid iterative method and shortcoming of classical ones, and what are we going to do? What are we supposed to do with LFA? Okay, so the goal of LFA is rather important to understand. It's to determine the smoothing factor for the smoothing operator SH. These are two manifestations of smoothing operators. This is GS Lex, that one is omega Jacobi. By smoothing factor, what do I mean? So be very attentive through this short bit, at least. I mean, those who are asleep, wake up. We just discussed that the operator is diagonalizable, has as many linearly independent eigenvectors as the number of columns. And it completes a basis for the corresponding Euclidean space. Now, what exactly happens? We dub one of those sets, the low frequency set, and the other as the high frequency set. We've already observed, we've cheated on and observed, that the high frequency eigenvectors get diminished very quickly, get smaller in magnitude, they decay very quickly with classical iterative methods of this sort. And low frequency ones don't. We're not bothered with the low frequency ones for the moment, but we still want to know how good a smoother is doing, how rapidly it would reduce the high frequency components. So if we were to find the spectral radius, the largest positive absolute eigenvalue of the smoother corresponding only to those eigenvectors that belong to the high frequency component, this particular spectral radius is dubbed as the smoothing factor. If we use all of those eigenvectors, the low frequency and the high frequency ones, we know Okay, low frequency ones, on those it would stall. Then the entire set of eigenvalues, the largest one of these absolute eigenvalues, the spectral radius over the entire spectrum, is known as the asymptotic convergence factor of those iterative methods. So we already know that it's poor. We're not bothered with the asymptotic convergence factor of the classical stationary iterative method. We are content in as much as it's less than 1, meaning the method we've constructed ain't divergent. We don't want a divergent method. We want a convergent method. We can deal with slow convergence in another way. So we are constructing a device that would handle the slow convergence, but we should be assured that the method ain't divergent, smoother. So LFA helps us determine smoothing factor for SH, which is this smoothing operator, and two grid convergence factors. Two grid convergence factors is the largest absolute eigenvalue of this, the spectral radius of the two grid operator, and the reduction factor of this is its spectral norm, or the 2 norm. Okay, it tells us how much magnitude of the residual it would reduce per cycle. Okay, and these are what the symbols mean. This is what the symbol means as well. This is the smoothing factor. This is the spectral radius of the two grid operator. It would tell us about the convergence, and this is the error reduction factor. Spectral radius tells us about this spectral radius would tell us about the asymptotic convergence behavior of the two grid method. And this guy would just tell us what happens, the error reduction factor in one step of the iteration. Okay, now this bit, which I have already gone in a little bit of detail, since the fundamental quantities are defined on the infinite grid, the influence of boundaries and of boundary conditions is not taken into account. At first, it might seem like a very serious drawback, but it isn't. LFA's idea or LFA's generality or robustness is compatible to all of this, neglecting the boundary conditions, in the sense that the objective of LFA is to determine the quantitative convergence behavior and efficiency an appropriate multigrid algorithm can attain if a proper boundary treatment is included. So we're not bothered by the boundary operators because the application of those is just a little bit. There are few operators there. You have had too much. Okay. So let's discuss a bit of terminology which we'd use in going ahead with this. I have a short question here, by the way, before I start on with this. And it's basically meant for those people who are doing some sort of a project, interesting project. It could be a work they're doing on a research paper, maybe faculty members or grad students who are working on some kind of partial differential equations. How many of you at some point in your research want to solve a PDE and would also be content if a closely approximate numerical solution was offered to you? Yeah. Okay, but you're dealing with the Schrodinger's equation or some manifestation of it, no? All kinds of equations. And I'm also interested in knowing what you're doing, Samreen and Kuratulan, or just a small brief.
So basically these are like, yeah, that would be great, because what I'm working on, I use these kind of periodic boundary conditions as well. So we make such lattice models, and then we make this periodic boundary conditions and try to solve that.
But you have to lace the periodic boundary conditions by some other boundary conditions as well in order to make the null space non-trivial, right?
Green is not solving Gaussian difference in
Yeah,
equation.
Okay.
just some
All right.
partition function.
Okay.
But
Semi-definite one.
Semi-definite. You are always a sadist. I knew it from the first day. So, how do you deal with the zero eigenvalue there? So if it's a semi-definite problem, every now and then the zero eigenvalue would tell you that it exists. And how do you handle it?
We'll try to take this dual and then we both come to the same solution nearby, then so okay, that's the problem.
Okay. At some point, you were working with Hodgkin-Huxley. You're not anymore. Okay. Oh, you, both of you, I know already. All right. So my only point is that I can see that some of you are interested more than others are, and I just wanted to know if numerical PDEs interest you. This boldface H is a small vector. H1 is the mesh size at the top line, mesh size along X, and H2 is the mesh size along Y. It's a fixed mesh size. It's not a variable mesh size. It's not a logarithmically varying mesh size, small, slightly larger, 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 and very fat. It's not like that. Okay, so in one dimension, H1 is constant. In the other dimension, H2 is constant. Okay, we associate an infinite grid G sub H. G sub H is written in the form of a collection of points, a set which contains this boldface X. This boldface X is an integer times H, and that integer is a positive integer. What it means is K1 H1 comma K2 H2, these ordered pairs, these Cartesian ordered pairs of all the grid points inside. We consider a discrete operator LH. Discrete operator LH, who remembers the finite difference, simple finite difference discretization of the 2D Laplacian, has a 4 in the center and has left and right and north and south neighbors as -1 and a 1 over h square outside. So the positions are represented by kappa, and the numbers themselves, -1 by h square, 4 by h square, they are represented by s sub kappa. And when it's applied, say, to a grid function, so WH is merely a grid function. By grid function, I mean a discrete function that has values only on the grid points and not in between. So when you apply such a discrete stencil to WH, this is what you get. That's how you open it up. You apply it position by position to your to the values of that the grid function has at those grid points. Okay, these are the fundamental quantities, the boxed one in 4.2.3. So for our 2D estimate, you remember for rigorous Fourier analysis, we had the product of sines. Here we have the product of these two complex exponentials. It's initially written as that e raised to the power I, the complex unit, and theta dot x by h. So x by h is one quantity. And I know some of the people I knew at Delft were not happy with this kind of representation that are in this book. So x is a vector and h is a vector, and it's a special construct that just tells you that it's x1 by h1 comma x2 by h2. This is what exactly it means. Nevertheless, you can see that it's a dot product, and if it's a dot product, it just opens up as the product of these two exponentials. Stark difference with what we did in rigorous Fourier analysis is how frequencies are laid out. What do you remember about the rigorous Fourier analysis from the second talk? That you had k and l varying from 1 to n minus 1. From 1 to n by 2 minus 1, you had low frequencies. From n by 2 to n minus 1, you had high frequencies. And if you had a pair, a frequency pair was dubbed low frequency only if both k and l components belong to the low frequency portion, 1 to n by 2 minus 1. if any one of them extended into the high frequency one while the other one didn't, we'd still call that a high frequency component. Okay, so the first thing that you recognize is that although theta, the bold-face theta, varies continuously in R square, it's not really necessary to consider entire R square from negative infinity to positive infinity and an infinite square, because these two frequencies for x belonging to the infinite grid would be equal if they are at a difference of 2 pi with each other, because of the periodicity of the sine and the cosine functions. So these functions, it's just enough to consider these functions on theta restricted to this set where they will have unique values. Outside of this, the values would get repeated due to periodicity. Okay, so these are the fundamental quantities. While this is the Fourier space. Okay, the first is a lemma, and we are very confident that the proof of this lemma is very straightforward, so we won't indulge in it, but we can easily work it out. For theta belonging to the range negative pi to pi, all grid functions phi are formal eigenfunctions of any discrete operator which can be described by a difference stencil. Okay, now as soon as it's quite easy to misread this lemma. It's quite easy to think of a multiple scale smoother such as the red black smoother or the red green black smoother or 4 color smoother, 4 directional smoother, and say, okay, life seems easy if this is just the eigenfunctions of those fancy smoothing operators in a straightforward way. That is not what is meant here. An extremely important stuff, a bit not enough highlighted in my opinion, is that it is only an eigenfunction of an operator which can be described by a difference stencil of this sort. Okay, if you think of this stencil, then all of your averaging operators, your interpolation operators, all of those, the injection restriction, the full weighting restriction of order 2, 3, 4, 5, whatever. There is another one, the prolongation operator, bilinear, bicubic, biquintic, and so on. They're all represented by stencils of this kind. So we can be at ease to a certain extent that anything which could be defined on one grid by a different stencil, these functions, the eigenfunctions of fundamental quantities, are the eigenfunctions of those. And it's rather simple to work them out. So you have, for example, LH. You apply LH to these eigenfunctions. What you get is you get a constant out, which is exactly equal to the application of these on the stencil elements. Okay, whenever you see a quidel or a tilde on top of an operator, you think of it as a formal eigenvalue. When we say formal eigenvalue, what do we mean? Or eigensymbol or formal eigenvalue? Formal eigenvalue is when you have just a stencil operator and not some entire matrix operator. So you can always apply the stencil to an eigenfunction and calculate out its corresponding eigenvalue that we call the formal eigenvalue, because it ignores all other things, it just works on the interior stencil. So the quidel on top with the LH is the eigensymbol or the symbol or the formal eigenvalue of LH. This is one example. That same operator, this is the operator that is used here, 1 by h square, and you have, when you apply it to I theta 1, basically x 1 by h actually becomes I times h. So this h and h cancel out, and then you have, in the same vein, theta 2, you are left out with j. So you could say, in a certain manner of speaking, that this grid function is resting at ij, and 4, the stencil element 4, is getting multiplied with this stencil element. If you wish to apply this stencil element, negative 1, for example, what you would consider here is not I, but I minus 1. J would stand as it is. Similarly, for this negative 1, you would multiply this using j I minus 1 and keeping j as it is. So varying this gives you, in a rather straightforward way, these eigensymbols that you can see. And simplifying these gives you this cosine function. You also have a coarse infinite grid where the mesh size has doubled along each dimension maybe, or there is some rule which tells you how to come up with a coarse grid which has a fatter mesh size. Okay, now we are moving on towards, we've done the terminology, the fundamentals, and now we are going to touch upon the harmonics. So for the smoothing and the two-grid analysis, we have to distinguish high and low frequency components on GH with respect to GH. So this is not to be underestimated in any way. This is an extremely important thing here. Coarse low frequencies and high frequencies are always contextual, meaning it depends on the coarsening scheme that you have. And it's also, in a certain way, it has the analysis has kind of a cyclic insight. You need to use many different coarse grid coarsening schemes in order to find out which coarsening schemes suit your problem. Once you have that coarsening scheme, you know what kind of frequencies what kind of low frequency regime you get. So for example, if it wasn't mesh doubling, which is the standard in the industry, it was mesh tripling, you would not use theta restricted between negative pi by 2 and pi by 2. You would use it between pi by 3 and negative pi by 3 and pi by 3, for example. Okay, this is a very important property when we come to low frequencies and high frequencies. It is saying that these two would differ if and only if the difference between these was pi. Now, at first it looks complicated, but it gets resolved as soon as you see this Fourier space picture. So this frequency is the one that you have in the low frequency space. And all the frequencies that differ, because the white box inside has a net length of 1 pi, or pi. So anything that differs by a difference of pi from it would lie in the high frequency space. So this is exactly what we need here. We would walk only on chop up all the low frequencies, pick up ordered pairs there. For each ordered pair, cook up 3 more frequencies, which would be in the high frequency regime, do an analysis, save a number. Do the same for all the low frequencies. As soon as we've done that, we have all the norms and estimates that we need. This is the definition of the high frequency and the low frequency for standard coarsening. When we say standard coarsening, we mean to say mesh doubling along X and mesh doubling along Y, which would give you, for vertex-centered grids, hierarchical grids. Hierarchical grids mean that all the coarse grid points are also shared by the fine grid. The fine grid only points may just be fine grid only points, but all the variables on the coarse grid are also available on the fine grid. There could be non-hierarchical grids as well. The first example of non-hierarchical grids would be when you have a cell-centered discretization setting. When you discretize using the same choppings of the domain, but instead of taking up the nodes at the intersection of the horizontal and vertical lines, you just take the centers of the cells. Those are non-hierarchical grids. They are analyzed differently. So smoothing analysis 1 and smoothing analysis 2. In smoothing analysis 1, we consider only one grid smoothers, like Jacobi, Gauss-Seidel, SOR, SSOR, and so on. We don't do red, black, Jacobi, multicolored variants of Gauss-Seidel in smoothing analysis 1, because there the invariance setup of the functions is subtly different there. And for the purpose of this talk, I believe it's enough involved to just deal with smoothing analysis 1 and then do coarse grid, two grid analysis based on smoothing analysis 1 and move on to H-ellipticity directly and show you some results. Okay, so for one grid methods, first thing to understand is how 4.3.1 is set up. Any smoothing method which only works on a single grid may be summarized in 4.3.1, which has kind of a stencil. What does it say? It says that you could write up the entire iterative step as this equation. LH super plus and LH super minus are splittings of the main operator. So in this example, for example, this thing here is LH super plus. This one here is LH super minus. Without this, of course, you kill this guy, you purge this. Or maybe I could write it just in the manner that when you have this, for Jacobi, this is LH plus, this is basically LH minus. Okay. Now what does it tell you? Where WH corresponds to the old approximation of UH, approximation before the relaxation step, and WH bar represents to the new approximation, which is the approximation currently at which you stand or just after one relaxation sweep. In this case, the relaxation is characterized by the splitting, and as soon as you have this splitting, you can see directly that Gauss-Seidel lexicographic is given by this. So if we add up the two, we get LH, that we know. And the Gauss-Seidel lexicographic step is written right there on this board, fourth line from the bottom. What we need to do exactly is, I'll show it to you because this is a bit instructive. The key point in getting or obtaining or determining LH plus and LH minus for any given single grid stationary iteration is to isolate this buddy here. So what do? We say, fine, take this on the other hand side. And what do you get here? BH plus UH, get rid of this, take this to this side, D minus L minus U, UH is equal to BH. And what you have now is, on this side what you have is your LH plus, and whatever you have with the older manifestation, K minus 1, K, what you have with this one is LH minus. This is what we do generically. If we are loaded with this step, we need to isolate the right hand side, work backwards, take a few reverse steps, and get the splittings easily. Now with Gauss-Seidel, you might think that this was a very trivial step. Why even have to show this? But I'll just show you successive over-relaxation. It is a little bit more involved than this. Okay, so these are the splittings. But first we need to know, before we go on to SSOR, which is a bit more ambitious, what we need to know is, what do we do with this LH plus and LH minus? Okay, so for now, hold that for a bit. This is just 3D omega Jacobi. These are the splittings. You can get these splittings for omega Jacobi. As soon as you add them up, you get LH back again. Okay, now subtracting the original one, 4.3.1, from the discrete equation given out as this, we obtain the local relation LH plus VH bar plus LH minus VH is equal to 0, which leads us to VH bar is equal to SH times VH for the errors. Now these are the errors. How do we know that VH represent the errors? Because if we find out the original approximation, we subtract the original equation from the approximation, we get an expression for the error. So the error is VH, the right hand sides, FH, they cancel off, giving you 0 on the right hand side, as you can see in the highlighted portion. So SH is the resulting smoothing operator. And from this, we immediately get the infinite grid Fourier representation of LH minus, LH plus, and SH. Applying LH minus and LH plus to the formal eigenfunctions, you apply them and you find out their corresponding symbols. So these are the corresponding symbols. And if you know that your smoother is a one grid smoother based on a difference tensor, then you can always say that the eigen symbol expression for the smoother SH, जिसके ऊपर tilde है, is equal to this fraction, negative LH minus formal eigenvalues of this, the symbol of this, divided by the formal eigenvalues of the portion that you invert. Okay, I have a question here, just to give you a nudge to wake up. Now 4.3.6. Think about that. May I have an LH plus that includes a diagonal on a 0 on the diagonal. This is an iterative method, right? I am constructing an iterative method. This is the iterative method. This is the strictly without the diagonal lower triangular part. This is just the main diagonal, and this is just the strictly upper triangular part. This chalks out Gauss-Seidel lexicographic for me. Now think about the eigenvalue expression for the smoother. May I have a 0 on the main diagonal in the part I choose to invert? Look, there are many catches, okay? So don't get perplexed, don't get entangled in those catches. There are many catches. For example, you could say the original problem was n cross n. The presenter chose not to invert this, otherwise I'd have a solution in a trice. Now, Muzaffar. So Muzaffar might be wondering, ठीक है हमने linear algebra किया था, उसमें तो हम एक ही step में जो है उसको A inverse right hand side लिख देते थे, तो what's the ado about this? यहाँ पे भी तो वही केस है, ये भी तो एक n क्रॉस n मैट्रिक्स है, इसको हम इन्वर्ट करके इससे मल्टीप्लाई कर रहे हैं, तो ये इटरेटिव स्टेप कहाँ पे हुआ? ये तो वही काम नहीं कर रहे तोड़ मरोड़ के. द आंसर इज नो, ये वो काम नहीं है. दिस कैन बी डन वेरी क्विकली इन अ फॉरवर्ड सॉल्व. फॉरवर्ड सॉल्व का क्या मतलब होता है? फॉरवर्ड सॉल्व का मतलब होता है कि जो इसकी पहली इक्वेशन है उसमें सिर्फ एक वेरिएबल है, आसानी के साथ राइट हैंड साइड को उससे डिवाइड करके उसका सोल्यूशन निकाल लें. जो सेकंड है उसमें पहले और दूसरे दो वेरिएबल्स हैं, बिकॉज दिस हैज़ अ लोअर ट्रायंगुलर स्ट्रक्चर, सो यू डोंट एक्चुअली हैव टू इन्वर्ट इट यूजिंग दैट agonizing way of inversion. I mean, anything that gives you an inverse of a matrix is agonizing, whether it's some kind of a lower upper setup or whether it's some other thing. But once you do have a lower triangular part, inverting it is order n. It's no big deal. You can quickly do it. Okay, now having said that, I'd come back to the question I posed. Why may I have a 0 on the main diagonal? Okay, the quick answer is no, you may not have a 0 on the main diagonal, because if you have a 0 on the main diagonal, what would you have? It's a lower triangular matrix. A 0 on the main diagonal would mean a 0 eigenvalue. A 0 eigenvalue, these are the eigenvalues. Don't forget the quiddle on top. If you have a 0 in the denominator, your smoother may not be convergent anymore. Okay, so you have to have something that you could uniquely invert in the LH plus part. Nevertheless, the highlighted portion 4.3.6 tells you that you have the eigen symbols of a smoother. What do I do with those eigen symbols? What do they depend on? They depend on theta. If I restrict the theta to the high frequency part only and find out the largest absolute value of SH quiddle on top, absolute largest eigenvalue, the spectral radius, where theta has been restricted to that upar wali patti, the high frequency part, what would I get? The smoothing factor for the smoother. Okay? Now this was not straightforward with the rigorous Fourier analysis, as you can revert and check. For example, for Gauss-Seidel lexicographic, what do we have? हमने दोनों के सिंबल्स कैलकुलेट किए. फर्स्ट वी कैलकुलेट द सिंबल ऑफ LH प्लस. वी सब्जेक्ट LH प्लस, वी सब्जेक्ट EI theta dot x by h to LH plus. It's that operator, we apply it on that and get the eigen symbols. Fine. We leave out this part. The eigen symbols, इसके eigen symbols इसके ऊपर क्वेडल लगा हुआ है, ये रहे. So if this is LH plus, what these guys represent is this LH plus के लिए. Similarly, this is given out by, if we apply this, this is what you get. The other operator, then you get a function. The eigen symbol expression for the smoother SH tilde is given out by this fraction, and we need to optimize this fraction. We need that supremum over the high frequency region. Our good luck or bad luck is that we said, fine, rigorous Fourier analysis was discrete. We could run a loop and catch the max. But now, since we have said that theta varies continuously, we are kind of in a more mathematically painful situation where you have to do, some magic in order to come up with the supremum value and the point at which the supremum occurs. We, on the other hand, the guys who actually do scientific computing, and if they need to have some sort of an estimate for the smoothing factor, we just do it the computational way, which means we mimic a continuous variation of theta by having, let's say, not just 4 but 4 million choppings of the entire space, making up frequency points, and doing a fast computer loop to check out the max value. This is what I have done all my life, but I realized today that I've missed something great. So let's check it out later. All right, so we can get the smoothing factor doing that. The smoothing factor is defined. Why do we call this spectral radius? These are just eigenvalues, right? SH tilde are just eigenvalues. So if theta is restricted to T high is that surrounding region of the high frequency space. So if theta is restricted to the high frequency space, what you get basically is the smoothing factor. If you don't restrict theta, if you let it vary in the entire frequency space, what you get is the asymptotic convergence factor of the smoother. Meaning, how would the smoother fare if you were to run it, say, 4 million times in order to crunch the problem all by itself? All right, so yeah, the supremum for GS Lex with the Laplacian problem turns out to be 0.5, and I'm told that this is the culprit frequency at which the max occurs, or the supremum occurs. Pi by 2, arc cos 4 by 5. Similarly, you can do pretty much not identical steps, but the procedure is nearly identical. The operators LH plus and LH minus differ. The only difference is how you define LH plus and LH minus for a particular classical smoother in order to subject that particular operator to those fundamental quantities, obtain symbols, and then create a fraction of the symbols. Invertible part का symbol denominator में आएगा, multiplicative part का symbol LH minus का symbol numerator में आएगा. There's a leading negative sign outside, which is immaterial since you already always compare the absolute values. SOR or omega GS Lex. So what is successive over-relaxation? Most students who get exposed to omega Jacobi, the matrix way, tend to extend the same omega averaging to a GS Lex iterate in pretty much the same way. I believe I've done it, Zulfiqar has done it, Shanila has done it. We all bump into that one simple error before being told कि GS Lex में averaging इस तरह नहीं होगी, point by point होगी. So GS Lex में inversion जो है, it's happening, it's not just a single diagonal inversion. It's not a reciprocation of the elements on the diagonal. It nevertheless involves an inverse matrix. Okay, so when that happens, you cannot say, fine, let me call this entire vector z, as I've done second line from the bottom there, and let me just average it this way. That doesn't happen. I mean, it's not omega GS Lex. Omega GS Lex, in omega GS Lex, you have to find out iterates point by point and over-relax or average them out using the previous point's value point by point. When you, however, envisage that in a matrix way, what you get is what I have written out from templates for your convenience here. So this is a matrix-based SOR step. It involves an omega. This is a successive over-relaxation step. And as you can see, it's not just doing it the Jacobi way, doing Gauss-Seidel the Jacobi way. Okay, now इसमें से if I have to find out LH plus and LH minus, as I discussed a few minutes ago, what must we do? We must isolate the guy BH. So this is the guy B in the extreme right. So to identify LH plus and LH minus, the first thing we do is to isolate B. When we isolate B, what we get is this quantity right here, and whatever is with the newer iterate is LH plus, whatever is this with the older iterate with a leading negative sign is LH minus, meaning the negative of that thing highlighted or underlined in green, the negative of it is LH minus for SOR. Now, this is what I can easily write if you check this out closely. So take a snapshot, think about this. This is exactly now written out in this fashion. This is the lower triangular part, this is the upper triangular part. Yeah? Can you register this? There it is. I can even copy paste this for your convenience. This is the part you see right here. And sorry, this is the part that you see with this one. So D is just 4 in this case. The diagonal element is 4 for the Laplacian. That's why you see the diagonal element as 4. Okay? This is how we construct LH plus and LH minus. So the only, it all tells you, it solidifies the fact that local Fourier analysis simplifies your smoothing analysis a great deal for a whole variety of smoothers that have two properties, work on one grid, they don't work across a scale of grids, and they could be represented by a different stencil. If that's the case, you can easily analyze their smoothing behavior. Okay, now we formally start with two-grid analysis. The first thing we realize is that it is kind of an adaptation of the rigorous analysis, but with the fundamental quantities that we use in LFA instead of the sign product of sign functions. So MH to capital H, and after a while I believe the author would say, ठीक है अब थोड़ी देर के लिए capital H छोड़ के let's start 2H, because then capital H has complications. Nevertheless, 4.4.1 is kind of generic. K H to 2H is just this operator. This entire thing is MH to 2H. And in order to calculate convergence factors and other relative quantities of MH to 2H, we will analyze how each of those specific components act on the Fourier components on the fundamental quantities, which is the product of exponentials here. And this analysis uses the fact that quadruples of those fundamental quantities, they coincide on the cost grid. All right, now it's not just to catch you unawares, but it's just to, again, give you a slight nudge in case you have forgotten it. In the second talk, when doing the rigorous Fourier analysis, we said that we have 4 functions. If you remember those 4 functions, they were those 4 functions: phi h k l, phi h n minus k n minus l, negative phi h n minus k l, and negative phi h k n minus l. These functions, they all had this inside them: xy, 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 and xy, and xy belong to the fine grid. They were all linearly independent functions. And we said that when xy belongs to the cost grid, we have all of these equated up to a sign with phi 2h KL with just this one function, where xy belong to this. In pretty much the same vein, I mean, there is hardly any difference if you see this closely. Quadruples of the fundamental quantities, the product of exponentials that we have now, coincide on the cos grid. For any low frequency, theta 1, theta 2, belonging to T low, which is that smaller inner square in that frequency diagram, the inner one, we consider these 4 frequencies. The indices have been chosen, the superscripts have been chosen with care. 0, 0 is the low frequency. 1, 1 is the high frequency. So what do you think theta 1 would be? Theta 1 bar would be in terms of theta 1? Either pi minus theta or theta minus pi, either one of those, depending on the original sign of theta. Similarly, theta super 1, 0 is theta 1 bar, theta 2, and so on. You have these 4 frequencies which coincide on the cos grid. And the bars are constructed by this formula. Theta I plus pi if theta I is less than 0, and theta I minus pi if theta I is larger than or equal to 0. Okay, now this is a lemma which could easily be proven. This is exactly what I was trying to motivate a minute ago. This one. The lemma says for any low frequency, theta superscript 00, which stands for the fact that this theta hails from the inner low frequency regime. We have these 4 frequencies equating, each of these 4 frequencies, they get equated to theta 0, 0 belonging to T low. This one. Each of these 4 frequency components, now we've unified all of these superscripts using the index set alpha. And we have said that the index set alpha consists of these 4 frequency indices. They coincide on G2H with the respective grid function given out as this one. So one of them has been proven by the author, and you can prove the other 2 quite easily. So harmonics for standard coarsening, these corresponding 4 fundamentals, also sometimes frequent. So there is a bit of an oversimplification which at times might perplex you a bit. In this jargon, the actual frequencies are the product of the exponentials. What's up?
Everything by
Okay, so actual frequencies are the product of those exponentials when the theta on which they depend hail from particular regimes. So if the theta hails from the inner square, we call that a low frequency, otherwise we call it a high frequency. But the theta pairs themselves are at times dubbed frequencies. I mean, the 2 terms are the same. So only the context would make it clear. What do you think is more appropriate? Calling those theta pairs frequencies or calling the product of the exponentials as frequencies? So think about the word frequencies. What do most frequencies resemble? Undulating sinusoidals. So those exponentials along with those frequencies, in my humble opinion, should be termed frequencies, but this mismatch is still there. At times you would find one author calling those theta values frequencies, and other times you would find those fundamental quantities being referred as frequencies. Okay, so you make capital E spaces in pretty much the same way as we did in the last talk with rigorous analysis with the product of sign functions. And we have the span of these fundamental quantities as E. All of these are formal eigenfunctions of LH. And under the assumptions made in the previous section also of SH, the operator HKH intermixes Fourier components with each other. This is a consequence of the fact that two different grids, a coarse grid and a fine grid, are involved. In the following, we will discuss this behavior in detail. And for that purpose, we consider an arbitrary function psi belonging to EH. Now, since EH is the span of those 4 frequencies, and by the way, when I say 4 frequencies, do you think there are only 4 frequencies, or there may be in many sets, each of whom is a tuple of 4 tuple of frequencies? Okay, so get things straight. It's that 4 frequencies are coupled with each other. ये जो 4 frequencies हैं, इनकी तकदीरें आपस में जुड़ी हुई हैं. ये नहीं है कि ये सिर्फ 4 ही हैं. The frequency space is a continuum, and there may be infinitely many 4 tuples. But the key point is, even though there are infinitely many of them, only 4 tuples matter. They all don't matter altogether at one time. If that was the case, the analysis would be impossible, I think. Okay, so if psi is a function, that belongs to capital E H sup theta, it could be represented as a linear combination of those basis elements, each one of them with an amplitude represented by capital A and doubly supersubscripted by the frequency elements. So we would analyze how the coefficients are transformed if the multigrid components in 4.4.1 are applied to psi, and we will treat each of the multigrid components separately in the following, but first summarize the results with respect to the coarse grid correction operator and the 2-grid operator. For clarity, we now write 2H instead of H. Okay. Now, what I am about to wrap up in a bundle and give it to you may leave you, if you are truly interested in it, a bit thirsty for getting a few of the reasons. But let me assure you that the reasons follow in a technically logical way, organized in pretty much the same manner in which I worked out each one of those with the rigorous analysis. So you can do exactly the same thing with this continuum analysis as well. Exactly the same thing, because you have just a 4 tuple. All right, so what is this saying? This is saying that the coarse grid correction operator KH2H is represented on EH2H by its symbol matrix. Okay, when you have, now let me explain to you something which for me as a student was extremely complicated. Okay, when I have simple matrix operators and I am estimating their eigenvalues, I use those squiddles. So those squiddles give me formal eigenvalues or eigensymbols. How do I get symbols when the representation matrix is different from the linear transformation? Now, the linear transformation may be given out in an entire different, maybe is given out in a simple Euclidean space, but its analysis takes into account a different space, which may be a 4-dimensional space which matters. Think of this in this way. So maybe what you have is a full dense 16 cross 16 matrix. In contrast, what you may have is 4 cross 4 blocks of this kind. So when you have eigensymbols of a matrix like this in terms of formal eigenvalues, you just call them eigensymbols and they're simple to understand. You use, for example, if this was LH, you use a quidel on top for them. However, when you have a representation matrix, the representation matrix for this entire linear transformation is a matrix in which only these 4 blocks matter. So if I have to represent the symbol of kh to 2h, where the representation is different from the actual linear transformation that it represents, I put a hat on top instead of a quidel. Just explaining how the symbols work here. Okay, so the cos-grid correction operator is represented on that by the symbol matrix hat kh to 2h. And how do I get kh to 2h? I have hats on all of these constituents. How do I calculate these constituents? I calculate these constituents, maybe what I should have instead, and let me make a small correction in this absolutely fabulous monograph, is this. Yeah, maybe this as well. So these are just ones. This is the identity matrix. These are actual symbols, and these are symbols where the representation matrix is different. How do amplitudes change when this is when kh to 2h applies on psi? Psi is given out as a linear combination of the 4 fundamentals. This symbol gets multiplied with each of the amplitudes, constructing an amplitude there. So if the spaces are invariant under the smoothing operator SH, then this could be represented as SH, where this transformation has the same, well, it preserves the space for all theta belonging to T low, and we also obtain a representation of M H to 2H on E H to H by a 4 cross matrix, 4 cross 4 matrix representing the symbol of the 2-grid operator. Okay, now what we can do is make macro observations. We can delve deeper into that, find out, no, we would like to work out each of those symbols. We could spend a rainy afternoon working out the symbols, and the symbols can be worked out. Symbols up to the biquintic interpolation operator and their natural adjoints, meaning full weightings of different orders, have already been worked out and are given in by Roman Wienand and Wolfgang Jopisch. It's a local Fourier analysis book, hardbound red book. It's given in that. A few are given in these books. The key point, however, is to understand how we might do this. We might do this by applying those operators to the fundamental quantities and determining the respective symbols and laying them out either in a 4 cross 1 row, in a 1 cross 4 column, or a 4 cross 4 diagonal matrix. This is exactly what we do in rigorous analysis. This is exactly what we do in local Fourier analysis. Now, this may be a bit perplexing for some of the pure mathematicians here. If we have a continuum, we have infinitely many 4 tuples. How do we handle them? Oh, I showed a simple continuum problem to a colleague, and I believe it was hard enough to spend a few minutes on it at least and work out how they might optimize it. But if you have infinitely many 4 tuples and you want a supremum over all of those, you can pretty much understand as a mathematician that it might be mathematically very difficult. I was taught in my student days how and when to use different words in a scientific way. So the first thing that my group told me is that you never use the word impossible in science. In science, it's a taboo word. You can use an abusive bad word, but you can never use the word impossible. Okay, so what do you say when you do think that something is impossible? You say it's difficult. Anything that is doable, however lengthy, however painful, however agonizing, is easy. So there are two things: easy, which is doable, without taking into account the amount of pain that it might induce in getting it done, and things that are impossible, you just call them difficult and put them on the side. So you may well think that if there is an infinite number of 4 tuples over which you need to optimize some function, the task might itself be a bit difficult. So what you do is you find a practical way of doing it. And the practical way of doing it is what numerical mathematicians often do. They chop up the regime on which the optimization has to be done so finely that it nearly mimics a continuum, though it's not essentially a continuum. Maybe billions of points, maybe trillions of points. They do an optimization by finding a max with using some intelligent algorithm, come up with an estimate of the supremum. This is the practical way of doing it. But if you want just to see the expressions are all there. Yes.
रिग्रेस कोलिजन एनालिसिस में हमारे पास ये 4x4 के ब्लॉक्स बन रहे थे स्मूदर्स की वजह से
नहीं, MH2 के लिए भी यही चीज़ बन रही थी.
कंबाइन करने पे ये 4x4 ब्लॉक बन रहे थे बट क्योंकि यहाँ पे स्मूदर्स के आइगन फंक्शंस भी हैं ये एक्सपोनेंशियल फंक्शंस तो फिर यहाँ पर ये कैसे बनेगा
यही चीज़ बनेगी. हार्मोनिक्स तो वही है ना, 0 0 1 1 1 0 0 1 जैसे ये वाले थे, KL n माइनस के n माइनस एल n माइनस के एल के n माइनस एल. हार्मोनिक्स बिल्कुल उसी तरह ही है. तो हार्मोनिक्स तो बिल्कुल वही है, ब्लॉक्स बिल्कुल उसी तरह बन रहे हैं.
वहाँ पे तो हम रिग्रेस में ये कह रहे थे ना कि हमारे पास स्मूदर्स के आइगन फंक्शंस नहीं है जो साइन फंक्शंस थे
मगर यहाँ हमने ऑलरेडी देख लिया है कि वो स्मूदर के आइगन फंक्शंस हैं और SH जो है, जिससे हम ये निकाल भी सकते हैं दैट SH क्वेडल थीटा इज नेगेटिव LH प्लस क्वेडल ओवर LH माइनस क्वेडल ओवर LH प्लस क्वेडल. वी ऑलरेडी नो दैट.
लेकिन यहाँ 4x4 ब्लॉक कैसे बने मुझे नहीं समझ आया ये मैट्रिक्स यहाँ पर कैसे आया
So the right way to unravel this is to think in which way you are thinking that this is different from the regress analysis. Think in terms of that. It's in no way different from a regress analysis. It just includes a battery of other methods that the regress analysis excluded. As far as procedure is concerned, it's the same. Yep. देखें, इस चीज़ को मत भूलें कि अगर ये केस भी आपके पास है, एक मिनट, अगर ये केस भी आपके पास है ना, तो इसको भी आप बिल्कुल उसी तरह एनालाइज कर सकते हैं. आपके पास आइगन वैल्यूज इस डायगोनल पे मिसाल के तौर पे चल रही हैं, ठीक है. यू कैन ऑलवेज से कि मेरे पास ये वाले जो हैं ये 4x4 ब्लॉक्स बन रहे हैं, डजेंट मैटर. इन 4x4 ब्लॉक्स की भी आइगन वैल्यूज यही आ रही होंगी. ये वाले इनवेरिएंट स्पेसेस से देखा था, ये डायरेक्टली आ रहा है. तो जब डायरेक्टली होता है तो वो भी इनवेरिएंट होता है. हर इनवेरिएंट जब ये डेंस है, जब ये पूरा डेंस है तो ये इनवेरिएंस से आएगा, ठीक है. ये डायरेक्टली नहीं आप इस तरह लिख सकते, लेकिन ये वाला जो है ये इस तरह विजुअलाइज किया जा सकता है. Does that answer your question? Any other questions? Do you have any questions? No. Zulfikar has got a bit wiser. He doesn't ask easy questions anymore. He makes sure he asks questions which I can't answer on the fly. Anyways, so 4.4.10 gives me the eigensymbols of the two-grid operator. And it simply means that if you write down this function, it may be written out as this. And you can always analyze mh to 2h hat using the 4 cross 4 matrices that we have. Okay, now there is a subtle point here which is important. We already know that we are considering exponentials, and the exponentials will collapse or vanish at particular frequencies. मगर क्या ये realistic situation है? The answer is no. It's not a realistic situation. It is an artifact that has been brought in by the grid being infinite without any boundary considerations. So in order to get a realistic estimate in our computer program, we make an allowance. We say, don't get startled, don't panic if you get a zero eigenvalue in the denominator. Capsize it, put it on the side, and proceed with the next eigenvalues, and only work with the non-zero eigenvalues. Okay, what I would now like to show you, so you can go on and find the symbols. Course, fine grid operator के symbols लिखे हुए हैं. आप different symbols restriction bilinear के निकाल सकते हैं, यहाँ पे भी दिए हुए हैं, और जैसे मैंने अभी आपको बताया Roman Venants में भी दिए हुए हैं. So you can check out those symbols, or you could work out those symbols if you get emotionally attached to the stuff, which I doubt a bit. That was a remarkable remark, by the way. सिर्फ फरमाइश की कमी है. Right, so these are the symbols of the bilinear interpolation operator. Right, as I said, as I promised, I would not go you through smoothing analysis 2 for red-black, at least in this talk. It merits a whole talk in itself. Because there is further invariance within invariance that you can exploit there. And instead of having 4 blocks, you can have literally work with 2 blocks. These are some results which the author has calculated for the W cycle, V cycle, GS Lex, and so on. What I am now inclined to check with you is the concept of H ellipticity. Where did H ellipticity go? Oh, it's ahead. By the way, these are some high frequency, low frequency sets that you would get in a frequency space if you had particular kinds of coarsenings. So if you have coarsening only in the x direction, you would define this entire set as your white set as your low frequency set, and the gray stripes on the sides are your high frequencies. Similarly, if you have coarsening only in the y direction for some problems, which is necessitated by when you have an anisotropic operator, you do it this way. If you have a checkerboard coarsening, red-black, you coarsen along the diagonals, your low frequencies become, they assume this diamond shape, and the gray triangles on the corners, they are your high frequencies. And if you reduce your entire grid not by mesh doubling or mesh tripling, but by mesh quadrupling, so you combine 4H and you make up just 1H in lieu of that, what you get is that you see one frequency aliases with 15 other frequencies in the entire set. All right, so the concept of H ellipticity. This is the last bit, and I'd surely let you go without further ado after I show you a few results. So the H ellipticities concept is based on LFA and also represents the LFA philosophy. When speaking of H ellipticity, we implicitly assume standard coarsening, H is equal to 2H, unless otherwise mentioned explicitly. This means that theta is a high frequency if theta belongs to T high, which is just that surrounding gray stripe. The H ellipticity measure EH of LH can be defined as the minimum absolute eigenvalue of the discretized PDE operator when theta is restricted to T high, multiplied with a scaling factor. Divided by that constant means multiplied by scaling factor to ensure that that number stays between 0 and 1. So max of L quadle is the absolute eigenvalue, maximum absolute eigenvalue in the entire region compared to that which it divides or scales the one in the high frequency region. So H ellipticity is a number which is between 0 and 1 after the scaling as 4.7.1, and you can easily write computer programs which would calculate H ellipticity for you in this manner. If H ellipticity is a number close to 0, the smoothing of your problem would be bad. If it's a number close to 1, the smoothing would be good. Okay, can you just look at the expression for H ellipticity and tell me what this magic formula or this magic potion is actually telling you? ये कब होगा कि 4.7.1 का रिजल्ट 0 के करीब आ रहा हो? Because this is exactly when point smoothers for your problem would not exist.
When you have small eigenvalues
For
for this
low frequency region. When you have very large eigenvalues for your low frequency region, this number would get tiny. If this number gets tiny, it means whatever you do with the high frequencies, low frequencies would keep, low frequencies are the irredeemable ones, which cause the method, the classical stationary iterative methods to stall. They would keep on dominating your problem. Your problem cannot be amply smoothed out using point smoothers. You may have other remedies. You may have Krylov subspace methods like conjugate gradients or some fancy cookup of GMRS or something like that. But simple classical stationary smoothers are not expected to work well. If you have corresponding to the low frequency eigenvectors in your definition of making the coarse grid, you have very large eigenvalues. One of the things now, just bear this small sidekick. One of the things that Zulfikar Saab had in his problem was that he was bumping in exactly the same issue. The smoothing, everything was bad. The coarse grid correction was bad as well. So we had some fancy restriction operator like the 5th degree adjoint of biquintic interpolation operators. Even then, the problem convergence wasn't good with standard coarsening. Because in standard coarsening, we say that in 2D, a quarter of the square is low frequency and all the rest is high frequency. But in that quarter, we had problems. We had very large eigenvalues. So we started on with non-standard coarsening methods. For example, we would say that the coarse grid mesh size was not 2 times the fine grid mesh size. It's just say 1.3 or 1.4 times the fine grid mesh size. That gave us non-hierarchical grids, but it started giving us a convergent multigrid method for the Helmholtz squared problems that he is tackling for his doctoral thesis. Yeah. So I'll quickly show you a few H ellipticity. So H ellipticity has to be bounded away from 0 necessarily. Good measure of H ellipticity कब होगा? When H ellipticity is bounded by a constant away from 0 is strictly positive. That is, H ellipticity sufficiently far from 0 for certain ranges of parameters on which LH depends. Heuristically, now, as mathematicians, what do you understand by the word heuristically? Yeah, heuristically is an admission that the math is too difficult for me to do there, so I would तुक्का लगाऊंगा मैं यहाँ पे. Yeah, so heuristically, an H ellipticity measure which is close to 0 indicates that very small eigenvalues exist for high frequencies. Okay, have a look at the standard 5-point discrete Laplacian on a square mesh. It's a stable discretization of the Laplacian. Its H ellipticity measure found in exactly this way is 0.25. ये standard Laplacian का कौन सा वाला वो है जो 1 over h square and standard stencil ये वाला होता है. Its H ellipticity measure is 0.25. This discrete operator is an order h square discretization of the first derivative. It's not H elliptic. If you use it, or if you use it to eliminate your boundary conditions, you must be prepared to suffer or lose some smoothing near the unknowns on your boundary, or near the boundary unknowns. However, the one-sided operator, this one, the forward or the backward one, both of them, they have much better H ellipticity and are superior to use. In many Neumann boundary value problems, it's not really very simple to find out why the problem is suffering. But in at least one of those, namely the convection diffusion problem, we know quite well that when we have the first derivative, the convective term in the operator, we need to use either the forward or the backward difference operator depending on the sign of the coefficient with it.
Sir, electricity 0.25 ये क्या हम upper bound तस्वर कर सकते हैं?
No.
किसी और जो operators हैं बाकी तो सारे operators इससे
No. The operators that reaction diffusion equations, which are the opposite of the indefinite Helmholtz, are much superior to Poisson. जैसे आप Helmholtz को कंस्ट्रक्ट करते हैं डायगोनल को एक नेगेटिव बायस देके, अगर आप नेगेटिव लाप्लासियन के पॉजिटिव डायगोनल में एक पॉजिटिव रिएक्शन टर्म ऐड कर दें तो जो उसकी डायगोनल डोमिनेंस है वो बहुत प्रोमिनेंट हो जाएगी, मच फास्टर. इफ यू मेक इट enough dominant, it may even mimic a direct solve. It may just solve it in 2 iterations or less than 2 iterations. Which is why there could be, you can artificially construct problems that have an H ellipticity nearly equal to 1. 0 से 1 रेंज है ना, तो ऐसे कंस्ट्रक्ट करना पॉसिबल है जस्ट जो 1 के करीब जा रहे हो.
लेकिन जो हमने प्रॉब्लम सॉल्व करने उसमें तो
Right. So there are many operators and you can find out the H ellipticity. कुछ ऑपरेटर्स जो मिक्स्ड डेरिवेटिव ऑपरेटर के ये वाली स्टेंसिल्स हैं ये एच एलिप्टिक नहीं है, ये वाली जो इसकी डिस्क्रिटाइजेशन है ये भी एच एलिप्टिक नहीं है, एंड सो ऑन. Are we So this is the fourth order Taylor discretization of the negative Laplacian. इसकी एच एलिप्टिसिटी 5 पॉइंट ऑपरेटर से थोड़ी सी ख़राब है, और वो ख़राब जो है वो इन एलिमेंट्स की वजह से है, इन एलिमेंट्स की वजह से। अगर आपका डायगोनल पॉजिटिव हो एक टोप्लीड्स मैट्रिक्स में, और ऑफ डायगोनल्स सारे के सारे मेन डायगोनल पॉजिटिव और ऑफ डायगोनल्स जो हैं वो सारे के सारे नेगेटिव हों, यू कॉल दैट डायगोनली डोमिनेंट, इफ इट्स डायगोनली डोमिनेंट मैट्रिक्स एंड एम मैट्रिक्स। एम मैट्रिक्स प्रॉपर्टी जो है वो इटरेटिव मेथड्स को बहुत ज़्यादा सूट करती है। देयर आर थ्योरम्स, पेरेंथ-फ्रोबेनियस एंड सम अदर थ्योरम्स विच एक्चुअली टेल यू व्हाई, बट इफ़ यू डू नॉट हैव एन एम मैट्रिक्स, यहाँ से एम मैट्रिक्स नहीं बनेगी इन पॉजिटिव ऑफ डायगोनल्स की वजह से। ठीक है, अगर डायगोनल सारे नेगेटिव हों और मेन डायगोनल पॉजिटिव हो, देन व्हाट यू हैव इज एन एम मैट्रिक्स if it's diagonally dominant. Okay, this is an anisotropic operator. This becomes non-H-elliptic when this epsilon tends to 0, and then there are different remedies on how to handle this, which is the topic of chapter 5. And I would just want to keep it this way, keep it up till here. We can check out later that smoothing suffers badly when H ellipticity hugs 0. We have a theorem and a proof ahead which tells us exactly how and why, but the gist of it is that we can always calculate the two grid factors, convergence factors, smoothing factors, and in pretty much the same manner calculate an H ellipticity measure for the operator that we have. If the H ellipticity measure is close to 0, we have a bad smoother, and then we need to work on what kind of remedies we need to make smoothing even better. I'll keep it up till this point, and in the next lecture, whenever it happens, the week or the next, we can talk about that. We intend to discuss a fundamental problem, the Helmholtz square problem, and I would ask one of the grad students here to give me a few results, H ellipticity and certain other results from rigorous and local Fourier analysis, which we could discuss. So what are the challenges ahead? By the way, don't get this misconception that multigrid is the only solution method out there. Multigrid only works with positive definite problems, for which we have smoothing procedures, or for negative definite problems. For indefinite problems, multigrid doesn't work alone. So it has to be used in conjunction with some Krylov subspace method, with some other method as a preconditioner. Sometimes multigrid as we know it is called geometric multigrid because it works on considering different geometric properties. For example, you must have seen that interpolation itself is a geometric procedure. Interpolating along x, along y, for example, in a linear fashion gives us bilinear interpolation. So if we just discard all geometric information and we start from the matrix equation, we'd have no clue if this was a PDE, a variational optimization problem, or some other sundry problem. That has led us to a matrix problem AU is equal to B that has certain properties. There is an entire different but related, philosophically related, not technically related battery of methods we could use. It's known as AMG, algebraic multigrid, which was constructed much later than the multigrid technique. And this book also gives out algebraic multigrid in the last few chapters. So this is one of the avenues where we might want to proceed in our different research projects and check out if implementing algebraic multigrid or using algebraic multigrid on our problem makes the problem or gives us any convergence that's better than geometric multigrid. Okay, with that I finish. Thank you all very much. Yes, Maz, I'm expecting something from you. No, not the project you have to submit. Now, regarding this talk.
Boundary conditions, symmetrics की eigen values को affect कर
आइगन वैल्यूज़ की सिमेट्री को?
अगर हम बाउंड्री इफ वी इम्पोज वेरियस बाउंड्री कंडीशंस विल अफेक्ट द आइगन वैल्यूज ऑफ द ऑपरेटर.
Yes, so boundary conditions when implemented basically change the matrix that you're getting. If the matrix has changed, its eigenvalues would change. Now, let me elaborate a little bit more on what you've asked. So, imagine that you have a symmetric circulant matrix, a symmetric circulant matrix. But once, and it has, since it's symmetric, it has all real coefficients, the eigenvalues are all real. However, once you implement the boundary conditions, if the boundary conditions are asymmetric, on one end of the domain, what boundary conditions you have the opposite signed boundary conditions on the other side, your matrix would no longer be symmetric. If the matrix is not symmetric, you may have a complex spectrum. So the answer is yes.
Theoretically क्या कोई theory exist करती है जिससे हम इस चीज़ को determine कर सकें कि boundary values हमारे operators को किस तरह disturb कर सकती हैं, boundary conditions. अब Fourier local Fourier analysis ने तो boundaries को exclude कर दिया. Regress में भी हमने शायद देखा है boundaries को या नहीं.
Okay, so let me try to answer your question. I am unaware of a regress theory which tells you if this is your operator minus the boundary conditions, how would particular boundary conditions impact a change in the spectrum. So I am unaware of any such theory. Maybe there is, maybe there isn't. But one of the key things, one of the key takeaways of the local Fourier analysis is that whatever boundary conditions you have, boundary conditions would ultimately translate into equations iterating on which would resolve your boundary unknowns. If that procedure is reasonable and convergent, then you don't need to worry too much on what impact your boundaries would have, because you can just work on the interior stencil and check out the convergence factors, say for a single iteration. And if the boundary iterations are damaging that, instead of one, maybe do 10 iterations on the boundary unknowns. Just do multiple iterations, and if those are convergent equations, a convergent iterative method, then the boundary conditions being very few compared to the interior equations, that wouldn't really impact a big change.
So you usually have Dirichlet, Neumann, or periodic, right?
Or mixed Robin boundary, or radiation boundary conditions as in Helmholtz, that absorb the radiations going out of the numerical domain.
But, I mean, you do get the eigenvalues and eigenmodes with these boundary conditions. If you
Yes, you can calculate, you can include those and get a grand
kind of special boundary
grand supremum on that. Yeah,
this theory.
yeah. So the key point is, say on the interior you get an eigenvalue C much less than 1, and on the boundaries for the same boundary iterations you get an eigenvalue D which is still less than 1 but much larger than C. The idea is to iterate as many times on D so that D squared, D cubed, D to the power 4 ultimately mimics C. That's the point of LFA. Anything else? Yes.
Yes, sir. Majorana 1 is the first quantum chip which is available for public use now, which is recent update by Microsoft. So, like, it means quantum computers are now accessible to normal human beings. So, when we will expose to that, so of course the mathematics will stay, but will these mathematical methods will still be useful for us when the quantum computing?
I can't guarantee that, because I was told that with the advent of a simple algorithm, I mean with the event of a simple algorithm run on a publicly available quantum chip, RSA was quickly broken. RSA has withstood 30 years of encryption and decryption. You know RSA, right? RSA is an encryption method. RSA heavily, so the key point is, think of 200 digits long 2 prime numbers multiplied together to form a roughly 400 digit long composite. But you don't know if that 400 digit long is composite or prime, and you need to, if you can factor it in.
Even if you know, you cannot factor it. Even if you know, it's
So you can't factor it in real time, but I've been told that with quantum computers you can do it. So, by the way, you have my legs shaking with that question. I don't know.